minutes. Some of the responses take less time. Actually, I don't know if any of them take longer than 15 minutes, but some of them you're definitely using the whole 15 minutes for. Some of them don't take quite as long. So again, this one for our warm-up was from 2016, so just a couple of years ago. They love to have one of these where they use the fundamental theorem of calculus. It seems to be a pretty common type of problem. They also like to have a free response where they give you a graph of either the original function or the derivative, and then they make you use information about that to justify things like maxes and mins and points of inflection. So this is a common type of free response. You're pretty much guaranteed to have a free response question in which you're given a graph and you have to answer questions about max, min, point of inflection that you have to use the graph for. Okay, so let's see. This is a no calculator question. And they tell us that the graph above is for the graph of f. And they give us that g of x equals the integral from 2 to x of f of t dt. Again, anytime you see this, pretty much they're probably going to ask you to do something with the derivative and the second derivative. So basically, as soon as you see this, go ahead and take your derivative, g prime of x. And as we talked about before this, fundamental theorem of calculus, when I do the derivative of an integral, I take my top bound, plug it in, multiply by its derivative, which would just be times 1, minus my bottom bound plugged in, f of 2, times its derivative, which would be 0. Whenever that's a constant, that always 0 cancels out, and f of x is 1 to f of x. So we should have somewhere in our paper g prime of x equals f of x. And then when we go to our second derivative, g double prime of x equals f prime of x. Now sometimes, and we've had problems like this before, your g of x is not defined just by the integral. Sometimes they'll do something like this, where g of x equals 5x squared plus the integral from 0 to, or maybe 2 to x of f of t dt. So sometimes they'll have something more. Again, just when you do your derivative, you would obviously take the derivative of this piece as well. So if I were to do my derivative here, I would have 10x plus, plug that in, we get f of x. And if I were to do my second derivative, I'd have 10 plus f of x. Okay, so don't forget about this piece here. All right, so let's go and take a look at what we have. The first question says, does g have a relative minimum, maximum, or neither at x equal to 10? So for min, max, or neither, what are we looking at? First derivative or second derivative? First derivative. Now I'm looking at g prime of x. So some common things to that people make mistakes on to be aware of is, first of all, in your justification, make sure you refer back to the function they're talking about. Never use the word it. Never use the word the graph or the words the graph. Always call the functions by name. If you say because the graph, well, what graph you're talking about? Graph of f, the graph of g, the graph of g prime. So always call the functions by name. The other thing too, a big mistake that I'm still seeing from some of you, is that we say that it's at x equal to 10. So let's suppose that we found out it was a maximum. Then I would say g has a maximum at x equal to 10. X equal to 10 is not my maximum. My maximum would be whatever y value is with it. We don't know the y value. This tells me the location of it. So make sure you're using the word x equal to 10. Okay. So for part A, we should have looked at our first derivative. Now for part B, it says, does the graph of g have a point of inflection at x equal to 4? What do we look at for our point of inflection? Second derivative, so I'm looking at g double prime of x. And again, we know g prime is just f of x. And g double prime is f prime of x. Okay. Now, for point of inflection, what has to be true about my second derivative? Because g double prime does what? Oh guys, you're making me nervous here. What's our justification beyond just second derivative? What about the second derivative? Changes signs. Good. So change of signs is what we're looking for. For max, then we have to specify the signs. Minimum, g prime changes from negative to positive. Maximum, g prime changes from positive to negative. Point of inflection, it just changes signs. It doesn't matter which way it goes. And then don't forget to always check when it equals 0, when it's 75. All right. And then absolute min and absolute max. Okay, so that's whenever we have absolute min, absolute max, it always is a little bit more work. Remember, we check our relative min and max. Min and max. And what else do we have to check? The endpoints. So we take our critical points, those are relative max and mins, our possible relative max and mins, and our endpoints, and then we actually find the y values for those. So that's where we have to actually find our y value. Alright, and then D is just talking about when g of x is less than 0. Okay, so I went ahead and grabbed the grading rubric for this. We can see how they went about grading this. Notice the very first point, g prime of x equals f of x, somewhere within your paper. Notice they didn't care where you put it, but as long as you had it in one of your parts, you got a point for that. So again, anytime you see this type of problem, almost immediately go ahead and write g prime of x equals f of x. And I would just go ahead and do the g double prime. Okay, so a point for that. For part A, we should have gotten that it has neither a relative min or max at x equal to 10. So it was neither, since g prime, which equals f of x, and f of x is less than 0 for all of us. So what you could have just said is that it doesn't change from positive to negative, negative to positive. Here they just specified because f of x, which is g prime, is always negative. But if you just said it didn't change signs, that would have been fine as well. So 1 point for A, your answer of neither with your justification. All right, for part B, our point of inflection. So again, it was 1 point here. 1 point for the that part of the g prime. Okay, for part B, it has a point of inflection at x equal to 4. In their justification, we say since g double prime, which equals f of x, changes signs. At that point, at x equal to 4. You could also say, because the first derivative is increasing to the left and then decreasing to the right. Okay, so that was just 1 point for your answer justification. Questions on A or B? Show me with thumbs how we did on A and B. Yay, there. Okay, overall, looks like this. Those of us that are here, do we have questions now? All right, now C, honestly, absolute max and min, I feel, are one of the bigger struggles for students. So just remember, we check our critical values and our endpoints. So we're going from -4 to 12. So that's why we have this guy and this guy. And then when we check our critical points, we've got -2 and 6. So our critical points come from the first derivative equal to 0 and the first derivative undefined. Remember, our first derivative is really just our f of x. Really just f of x equal to 0 or f of x undefined. So here they said it changed signs only at -2 and 6. That's our critical points equal to 0 and undefined. We have it equal 0 here. We have it equal 0 here and here and here. Now, why was I able to avoid checking 2 and 10? Why didn't I have to check this? It's fine if you did, but why didn't I have to check this? Yeah, it doesn't change signs. For a min, it needs to go from negative to positive. For max, it needs to go from positive to negative. So it has to change signs. Since these did not change signs, we know they're not going to be possible maxes or mins. Now, you could check them. You didn't have to. It was fine if you did. But the ones that were definitely potential candidates was -2 and 6. Okay, so you got 1 point for considering -2 and 6. So if you have this on your graph, that was 1 point, or on your chart. And then you got 1 point for considering your endpoints. So that's quite generous. All right, and then when we actually find our value, so to find g of x, remember g of x was just simply defined as that integral from 2 to x. So all you're doing is actually finding that integral for each of these. So when I go do my integral, I'm going from 2 to -4, from 2 to -2, from 2 to 6, from 2 to 12. So you just find your integral for each of those, adding your areas together. Keep in mind, if our bounds are flip-flopped, then that means we're going to have to switch them and negate it. So for example, for this one here, when I go to do g of -4, this would be from 2 to the -4 of f of 2 dt. I would want to go ahead and switch my bounds. So I would have g of -4 is the opposite of -4 times 2. Okay, so that's something to be careful with there. And when we go and find each of those values, then we end up finding that our absolute minimum, value is g of -2 equals to -8. Do they actually ask for the minimum values? Yes. Okay. So that's something to keep in mind. It actually asks for the value rather than just where it occurs. Okay. Now it's not a bad idea that when you say, when you talk about the absolute min, you could say the absolute min is -8 at x equal to -2. So you kind of cover both bases there. And then our absolute max was 8, and that occurred at x equals 6. So you got 2 points for your answers with the justification. The justification is our chart. So if you have your chart, then that's the justification. So C actually was 4 points. It was almost half of the points. Wait, do we have questions with C? Anytime they ask about absolute max or min, you must, you don't have to, but do the chart, because that will take care of your justification for you. All right, for part D, it asks when G was less than 0. All right. So G is less than 0. Again, we're looking at when our integral from 2 to x. So we want basically when the area underneath our curve from 2 to whatever value is negative. Okay, so I'm looking at 2 to whatever value. So if I were to go 2 to 6, that's obviously positive. 2 to 10, those cancel each other out, so that's going to be negative. But beyond that, I then have more negative. And now going this way, remember we have to do opposite because we're going backwards. So 2 to -2 would give us a negative area. And then going on to 4, that's not quite all of it, so we still have the negative area. So our answer for this would be from -4 to 2, and from 10 to 12. So 2 points for this, probably 1 point for this. Questions for that?
Why doesn't it have a negative area from 6 to 10?
So 6 to 10, we're going, our integral is 2 to whatever value. So 2 to 6 can be positive. This then would cancel it out. So at 10 we would be back at 0. Other questions with this? Okay.
Can you just, when you're doing the chart, is that based off the area under the graph?
Is it based on, yeah, the area from the graph? Mm-hmm. Yeah, so when we go to do like g of -4, then I'm finding the area from -4 to 2 and then negating that. So you're just looking, because it's the integral of f of t, which is the area under f of t.
So will you do it like -4 to -2 and find that area?
So when I do like, if I were to do g of -4, let me go back up here. So g of -4, I'm just plugging this into my integral, so let me right up here. I have from 2, my x value is -4, f of t dt. Now, you can either just go ahead and find the area from here to here, and because we're going from 2 to -4, we're going backwards, you could just do the opposite signs. Or you could rewrite this as negative of -2 f of t dt. So then you find your areas and just thinking that. Does that make sense?
Yeah.
Yes.
Doesn't from -4 to 2, it's not still positive, negative area is smaller than
So it's because, again, our integral is 2 to the value. So when we go to this way, it's going to be opposite of that. So our area above would then actually be negative, and our area below would then be positive. Does that make sense?
Yeah. Yeah.
So that's why it's, okay, so all of this I have the negative area, and you're correct, this isn't enough to cancel it out.
So when you go in the other direction, then
Yeah.
consider that, okay.
Yeah, you can think of it as, again, this, or you could just think, whenever I go the opposite direction, that's what it is. You can think of it. Other questions with this? Okay, so go ahead and grade approximately what you would get for this, so you can kind of get an idea of the score. And remember, it's out of 9 points. So usually with these problems, A and B are typically relatively easy points. A lot of times A and B are more than just 1 point apiece. They assigned a lot to part C. But all right. So that's just to kind of give you an idea. Again, giving free response to help us prepare for it. But that's just kind of giving you an idea. This is a typical type of free response problem that we have the fundamental theorem of calculus. We have the graph, and they ask you stuff about increasing, or not increasing, maximum, and points of inflection. Okay. Any other questions with that? All right, let's go take a look at our homework. So we have problems 9, 11, and 12 we'll take a look at. Alright, so it says find the solution of the differential equation that satisfies the given condition. Okay, so for number 9 here, let me just zoom in. Okay, so number 9 we always want to get y's on one side, x's on the other. So go ahead and add in your natural log of x over. And then I need to divide my x over, so I have that on this side, and I need to multiply my dx over. So we should have, let's zoom in a little bit more. Alright, so we should have y dy natural log of x over x dx. Now on our left side, it's pretty easy to integrate that. On the right side here, we do have to do a u sum. So when I go to integrate, if I let u be the denominator, which we often do when we have a fraction, it doesn't get us anywhere because then the derivative u would just be dx, and we don't cancel out our natural log of x. If we let u be the top natural log of x, our derivative is 1 over x dx. And so we can think of this integral as natural log of x times 1 over x dx. And that's what helps take care of that. Okay, so doing that little u sub then, on the right side, we end up getting for our antiderivative 1/2 natural log of x quantity squared plus c. And then on our left side over here, again, that was a pretty nice antiderivative of the 1/2 y squared. All right. Now, they did give us an actual particular solution here. So we can go ahead and find out what our c value is. So when we plug in 0 for our y and plug in 1 for our x, we end up, it's just 0 and 0, so our signs actually are the same. So we don't need to consider both. Our signs are the same, so we just take the positive of it. And we solve for c to get c is 0. So going back to our, we'll go back to this guy. So then at this point c is 0, so we just plug that in. So we have 1/2 y squared equals 1/2 quantity natural log of x squared. And then c was 0, so we don't have that. Okay, so now we just need to go ahead and solve for y. So I'm going to multiply both sides by 2, so we get y squared equals natural log of x quantity squared. Why did I say the square root? Oh. Okay, they didn't simplify that. So we have then y equals, when we take the square root, squared and squared would be natural log of x, but remember it's actually absolute value of this. Okay, so I don't know we talked about this in here. So back in algebra 2, they should have taught you that square root of x squared is the absolute value of x. Do we remember that?
Yeah.
Okay, so really, okay, I feel like some of you guys just said yes to saying yes. They literally in the back corner there. Okay, so square root and squared cancel each other out, but it's actually the absolute value of it, because we could have either positive 3 would be, like, so let's just say that it was the square root of x squared. We could have positive 3 would satisfy that, and negative 3 could satisfy that, right? If I have positive 3 squared, square rooted, that gives the same thing as the absolute value of positive 3. Same thing with negative 3. If I say negative 3 times squared is 9, squared is 3, absolute value of negative 3 is 3. So whenever you take square root of a square, we should have an absolute value. So technically, when we square root both sides here, we should have the absolute value. Instead of writing absolute value, you could write plus or minus. But we are only taking the positive one because our values are the same there. So we only need the positive piece of our piecewise here. So we really just have like this natural like that. So this was really just an unsimplified version. I'm not sure why they didn't simplify it. But we don't take both pieces. Because if I had both pieces, then I would have a top branch and a bottom branch in my square root. So we don't take both pieces, we take just one piece. So I would just have this. Questions? Oh, number 9. Questions with number 9. Yes.
I have a question on 8, since you're getting to
On 8, yeah.
So like, when you plug, before you like plug in the 0, 4, you move the 2 over, you have to move the 2 over?
No. You can plug it in right here. Yeah, so if you were to plug it in right here, then just when you go to put your C back in, you put it back in at this point.
Oh, okay.
Yeah, so wherever, guys, whenever you plug in the value, wherever you plug it in, when you solve for C, you have to go back to that point when you put C in.
For 8, it's positive and not plus or minus. It's just the value.
Yeah, let's double check. So when we put in 4, we got positive, so that's why we take the positive branch of it. Yeah. So guys, remember to decide whether we're taking positive or negative, when you put this in, so we put it in here, check both sides. If they're the same sign, then we take the positive of it. If they're negative, if they're opposite signs, then we have to do the negative version of it. So when we took 4 and put it in, we got a positive on this side. Took 0 and put it in over here, we got a positive on this side. Same sign, so we take the positive value. Okay. Let's go and take a look at number 11. Alright, so again, first thing we need to get x is on one side, y is on the other. So let's see, add your 1 plus y squared over. So this is a little different looking here. So then we have, okay, so this one took a little bit more work because we're so used to having our y's on the left, but so if we add our 1 plus y squared over, and then guys, you could treat this just like cross multiplying if you wanted to, or properties of proportions. But our properties of proportions is we can just flip the whole thing upside down. Either way. So anyway, we want to move one thing to one side and one thing to the other side. You never want to have 1 over a differential, so that's why basically multiply by dx on both sides. It's like gets rid of that. And then we would want to divide by my 1 plus y squared, so that's why you see in the denominator over here. And divide by your 1 plus x squared, so that's why you see in the denominator there. Okay, so you don't want to have 1 over dy. We don't ever integrate something 1 over a differential. Okay. So now at this point is where we take our integral. We got a double inverse trig. Sweet. Okay, so our antiderivative would be inverse tangent of y, antiderivative inverse tangent of x. Again, you only have to write the plus c on one side. And then our initial condition for this, our y value is square root of 3. So we're plugging in at this point here. Alright, guys, I think it's always good to specify that you're saying at y 0 equal to square root of 3. Just so that it communicates to the AP reader that, hey, I'm plugging in the point here. Alright, so we plug in our y value, plug in our x value. Now let's double check our signs. Inverse tangent of square root of 3. What is the value of inverse tangent of square root of 3? First of all, for inverse tangent, are we in this, the fourth and first, or are we in the first and second quadrants? Fourth and first. So we do have to consider whether it's a positive or negative. Inverse tangent of square root of 3. What do we get for that? Okay, maybe let me ask an easier one. Inverse tangent of 0. What gives me inverse tangent of 0? Tangent is sine over cosine. On my unit circle, where is sine 0? Good, 0 and pi, but we have to stay within these two quadrants. We're at 0. Okay, so we got that this one was 0. So now can you maybe take a look here? What was our inverse tangent of 3? Close. Oh no, wait, it's pi over 3. Sorry, I was thinking it was negative pi over 3. So pi over 3. So we have it positive. So this over here was pi over 3. So positive, 0. They're not opposite signs. 0 doesn't really have a sign. So they're not opposite signs. So we take the positive of this. We don't actually have to worry about different branches though, do we? No, because it's not a natural log and it's not a square root 3. Okay, that's fine. So we get c equals pi over 3. So guys, you do need to know how to do inverse trig. They will ask you about that. Alright, so we, again, because I plugged in my point here, this is where I go back to take my c and put it back in. Okay, so that's why you see we have inverse tangent of y equals inverse tangent of x plus instead of c pi over 3. Okay, so now to undo my inverse tangent, we just do regular tangent. So tangent of inverse tangent of pi of inverse tangent of x plus pi over 3. Now, I cannot simplify this because I'm adding within my argument. This is not just tangent of the first plus tangent of the second. So we can't simplify this anymore. That's our final answer. All right. Questions with number 11. And then number 12. Again, you had to do some maneuvering first. Let's see. Looks like t is our function that we're working with. So I want dt over, d capital T over d little t. Okay. So let's go ahead and just subtract this full piece over. So then I've got my dt on one side and my little t on the other side. K is just a coefficient. It's not an actual value, so I would leave it with my small dt. But I do need to get my big T over, so you're going to have to distribute that first. And that's why we have, I guess you'd have to distribute it. Never mind. We just divide this whole thing over. So that's what we had in the denominator here. Alright, so we have big T over here. We end up not having any little t, so that's okay. We just have that coefficient. So now when I go to do my integral, this should say to you, hey, probably a natural log, but we do need to do a little mini u sum. So if I let u equal capital T minus 70, then du would be 0 dt. So it ends up that it's just natural log, and my inside natural log of u, so would be t minus 70. We didn't have a coefficient. And then over here, again, k is not my variable. Little t is my variable. This is just a number. It's like saying the integral -5. So you could technically bring that out in front, and then we would have our inside derivative would just be t multiplied by my coefficient. Do we have questions as to how to get to this point here? Are we okay with that? All right. So now let's go ahead and plug in our initial condition. So at this point, looks like they didn't plug it in yet. Or did they? Right. No, they kept going. All right. At this point, I would go ahead and plug in my initial condition, but they kept going and went ahead and started solving a little bit more. So exponentiating both sides, we get e to this side. My e and natural log cancel out, so then I have just t minus 70. That should still be absolute value there. Okay. So at this point then we've got to substitute in. We can't drop the absolute value bar yet. Alright, so now when I go ahead and substitute in, I get, let's see, my t value is 140, so I have 140 minus 70, so this is going to give me a positive here. And when I take my 0, put it over here, I get a positive. Okay, so then that lets me know I'm going to take the positive version of this. Okay, so now when we solve, we end up getting c is 70. So again, we have to take the positive version of this, and I don't think, did you guys have to take the negative version of any of these? I don't think you did. It's possible that they will have you guys do that, but it's more common that we have the positive version. I don't think you had to do a negative with any of these. That's all right. Okay, so that's why we end up having the positive version. We cannot drop the absolute value bar until we've decided, so plug in your initial condition and decide positive versus negative. And then you can know whether to take your positive or negative version of your answer there. So honestly, I like to, as soon as I do my integral, that's where I like to go ahead and do my initial condition. Again, you can wait. I just like to do it there so I have numbers to work with rather than letters, variables. Okay. Do we have any questions with number 12? Yes.
I plugged in the ln of t minus 70, the 140. I got ln of 70c, so.
So you went at this point here? Okay, let me do that over here and just double check we get the same answer. So you had natural log of t minus 70. And what did you get for your c?
ln of 70.
Like that? Okay. So we plug it in, and then let's go ahead and solve for our capital T. So I'm going to exponentiate both sides. This is bad notation, but I'm just going to do that. Okay. So I have, and we said we're going to take, I'll go ahead and write absolute value bars. And then I'm just going to break this up so this will be times e to the natural log of 70. All right, now we said we're taking the positive of this based upon my initial condition. And then e to the natural log of 70 would just be 70, so I would have 70 times that. Does that make sense? Okay. So then I would have t equals 70 e to the negative kt plus 70. What they got here? Awesome. Does that make sense? So guys, wherever you plug in your initial condition, that's what you have to go back to when you actually solve your c. Put it back in there before you solve for your variable. Other questions with that? Okay, so let's go take a look at what we're doing for today. Today's topic is actually, I think, the second easiest topic in calculus. It's basically what you did in algebra 2 and 3 exponentials. Exponential growth and decay.
Can you send out an extra 3, please?
Yes.
Thank you, Conrad. I'll get an extra 2.
Okay, so what we're looking at today is exponential growth and decay. Okay, go and read that top part while I bring up the smartboard. Okay, so exponential growth and decay, the reason why this topic is so easy for us is because essentially we're just doing exponentials like we did back in algebra 2. But the reason why we have it in calculus is because that equation, y equals c e to the kt, or p equals e to the rt, does that sound familiar? Like the PERT equation? Where that came from is actually from calculus using our separable differential equations. So I'm going to show you how we do that, but then we'll just use the shortcut. All right, so if we have, whenever you see this statement, the rate of change of something is directly proportional to itself. Key thing here, directly proportional to itself. Then what that means is that my rate of change, so dy dt, we'll just say, right? We're talking about a rate, so dy dt is directly proportional to y. Now, back in Algebra 1, you learned about direct variation and inverse variation. And if something was directly proportional or direct variation, then that was that it was, so if y was directly proportional to x, we would say y equals k times x. If it was inversely proportional, we would say k over x. Learned this back in Algebra 1, and then you did a little more with it in Algebra 2. But when it says directly proportional, that means that we're just multiplying k times that value there. So my rate of change is my dy dt is, that means equals, directly proportional to y, it's just k times y. So that statement translates to this statement here. So this is a differential equation. We can actually solve this differential equation and find the original equation that gives us this, just like we've done before. And when we do that, they've done the work here for you. So we integrate both sides, right? Integrate both sides. We have natural log of the absolute value of y, and we have k t plus c. They go through and solve, and we end up with y equals e to the kt plus c, which is e to the kt times e to the c. We talked about last class how e to the c is just another constant, so that's what gets us this equation here. Okay, y equals c e to the kt. So this, we can use our shortcut. Instead of doing separable differential equations every time we see this, we can take the shortcut and say, hey, if we've got that it's directly proportional, again, directly proportional, then I immediately know that my antiderivative is going to be this. Y equals c e to the kt. On the AP exam, if they gave this problem, they don't expect you to do the separable differential equation. You can go from this immediately to that. You can take that shortcut, and they're perfectly okay with that. Now, this last line here, what they're doing instead of writing a big C for constant is they're saying, all right, well, that's our initial condition. So they're just saying if y sub L represents the initial condition. Okay. So again, this is whenever we have directly proportional. The rate is directly proportional to itself. So probably the easiest example of this is that when you put money in a bank, the more money you have, the faster it gains interest. So how much interest you gain, the rate of change of that money is going to be bigger as the more money you have, and there is also bigger. Another one that we're going to look at is talking about pressure in a tire. As air leaks out of the tire, the less air there is, the less pressure there is. Okay, so that's what it means to be directly proportional. If one goes up, the other goes up. If one goes down, the other goes down. Okay, so really, anytime we have directly proportional, we can take this and jump to this. Okay. So we really just use that to plug in values and solve. And that's all that we're doing for this. So we're pretty much, we use calculus to see the shortcut, and then we just use the shortcut for there. Okay, so our first example here, we've got a punctured tire. We run over a nail, bummer. As the air leaks out of your tire, the rate of change of air pressure inside the tire is directly proportional to that pressure. Okay, so rate of change of pressure is directly proportional to the pressure. Okay, so at the time of the puncture, the pressure is high, so air escapes quickly. As time goes on, there's less air, so air escapes less quickly. All right, so write a differential equation that states that fact if the pressure is 45 pounds per psi, and a decrease at the rate of 0.36 pounds per psi per minute at the time the nail is struck. All right, so again, let's go choose our variables. The pressure is P. All right, so dP, dt, the rate of change of air pressure is directly proportional to the pressure. Okay, so our differential equation just be dp dt equals k times t. And it's good for us to go ahead and define our variables. So P is the pressure of air and tire. And this is, what would that be, pounds or PSI? And T is time. And what are we talking about? Minutes. Okay. Alright, so we have pressure is 45 pounds per PSI and decreasing at a rate of 0.28. Okay, so now we're just really plugging and chugging. What's my rate? The 0.36, good. Sorry, minus 0.36. So I have 0.36. That's my rate. Now, is my rate a positive or a negative? Negative, because it's decreasing at the rate. The amount of air is getting smaller. So that's really important. Just like we had to do that with related rates, we still have to consider that. Okay? And then we don't know our coefficient K. But what's our pressure? 45 pounds. And then all we do is solve for K. A lot of times these are calculator problems. If it's not a calculator problem, it'd have to be a value you would know. But go ahead and pull out your calculator, punch this in, let's see what we get. Alright, if you, I know Monty's not here, so you're just going to calculator. It's Pi Day, which means it's your birthday! Happy birthday, Austin!
Happy birthday! Thank you. Welcome.
So much buy a slice of pie for his birthday.
Hey, you can get one for $1 after school.
Thank you, guys. Where?
In this classroom at Math Honor Society.
In the cafeteria!
Ian.
Okay, what's our K value?
Negative 0.00.
Exactly 0.008. Awesome. Okay, so let's write our differential equation. Our differential equation for this situation would be dp dt equals negative 0.008 p. Awesome. Now we don't have to really do anything just yet. We're just setting up the differential equation. So we just use our differential equation and that information to solve for k. All right. Now let's do more with it. Oh. Let's solve it. Okay. So we had dp dt equals negative 0.008 p. Is that what it was? Okay, so this is what our differential equation was. Now, let's go back here. Remember, our differential equation, our solution is always this. So we go back and forth. So I'm just gonna rewrite that up. Dy equals ky translates to equals c. Wait, remember this is our initial. All right, so solving our differential equation. So let's see, for us, our variable is P. What was our initial condition? How much air was there initially in the tire?
45.
45, thank you. And then we have E. What was my K value we just found?
Negative 0.008.
Negative 0.008 T. So again, you could have gone through, separated, integrated, and solved. But whenever we have that directly proportional kind, we can immediately jump to our answer using the shortcut. Okay, so it made it a lot faster for us to solve it. Okay, questions with B. Now C. What will the pressure be at 10 minutes after the tire is punctured? So now we just use this equation to solve. So now I have an equation for my pressure. Before I had an equation for my rate at which the pressure was changing. I used that to get my equation for my actual pressure. So now I want to know what will the pressure be at 10 minutes. All right, so I'm going to write P of 10. feel like that's better notation. So I have 45 e to the negative 0.008, and my time is 10, and we just punch that into our calculator. What do we get? Sounds right. 41.540, and what would our units be? Well, we're just looking at the pressure, so pressure is measured in pounds per minute. I feel like we don't need a slash. PSI stands for per square inch. I feel like you don't need a slash, but that's okay. We'll just put okay. All right. So a couple of things with this. I mean, that was really just all we had to do. But a couple of things. For our K value, it was a nice number that cut off. It was just 0.008. But let's suppose it was more than that, a big long decimal. When you go to put it into your equation, you do have to use the big long decimal. I know we didn't have one here, but you do have to use the big long decimal. So I would say when you find your K value, I would say store that in. You could do alpha K, you could store it in for X, whatever you prefer. But store that in so that when you type in your calculator, you can just hit alpha K. And then what was the other thing? Oh, when you get your answer, make sure it makes sense with our problem. So our original pressure was 45 pounds, we should expect that it is something smaller. If you would have forgotten your negative for your K value, you would have gotten something larger. And so it's always good to double check that your answer makes sense. If you got a bigger number, you'd be like, wait a second, air's leaking. We shouldn't have a bigger or higher pressure. Okay, so just little things like that can help save mistakes. Okay, the car is safe to drive as long as the pressure is 20 pounds per square inch or greater. For how long after the puncture will the car be safe to drive? Okay, what do we do with this?
And it's all for T, so you will.
Yeah, we want to find how long, so we want to find T. Okay, now they're telling us what the pressure is. It's allowed to be 20 pounds. So let's find out at what point is it 20 pounds, and we can know for that length of time. You know what? I think it's safe to drive it with less.
Yeah, I think so.
We'll go with it. No, we're not going to skip it. I just feel like we could have it less than that. It's probably not good to, but I think I've driven on less than that.
Yeah, you got more traction.
You have what?
More traction.
Yes. I mean, it's not good to drive on that, but you can drive home. It'll be fine. All right. So we have, again, our pressure equation. So we know our pressure is 20. 45 e to negative 0.008 T. Okay, we're trying to solve for T. At what point does it become 20 pounds? Up until then, we can drive. Okay. You have your calculator, but our exponential goes way off the graph pretty fast. And so it might be in your best interest to do a little bit of math beforehand. I don't know. It's up to you. I'm going to solve this by hand so we can remember how to solve exponentials by hand. What's my first thing that I do? Divide by 45. And then, so I have 20 over 45 equals e to the negative 0.008 t. How do I get rid of that e?
Natural log.
Yes, natural log it. I'm not sure what the technical term is. We're going to take the natural log of both sides. Exponentiate sounds so great. Natural log it sounds a little weird. Alright, so I'm going to take the natural log of both sides. So natural log of 20 over 45. And again, natural log of exponential, those cancel each other out, so I'm left with just my exponent, negative 0.008 t. So then my t is natural log of 20 over 45 divided by negative 0.008. Again, if you have your calculator, you can use it earlier on, but I want to make sure we remember how to solve exponentials. All right, what do we get for our value there? How much was it?
101.366.
101.366.
Yeah.
And that's minutes, so that's like an hour and a half, right? Over an hour and a half.
Yeah.
Ah, so you can drive for forever.
Tons of traffic.
Yeah, that's true. around here. In Ohio, you could drive for.
Yes, yeah.
Okay, and that's it. So again, the key things that we're doing, now this is not always what they're going to be asking. They usually will ask you something like D or C. So you have to work a little bit to get there. You have to first solve for your coefficient, and then write your equation and set that up using the power. Okay, let's take a look at our bacteria. Another common type of problem.
Bacteria.
Yeah, bacteria. Bacteria in a lab culture grows in such a way that the instantaneous rate of change of bacteria is directly proportional, shortcut, to the number of bacteria present. Okay, I'm going to say let B be the number of bacteria. And they don't specify time, do they? T is time. Looking ahead, I see that E asks for in hours. So I'm going to say in hours. And I'm looking ahead, I see that it says 3 million bacteria. Rather than writing 3,000,000,000, I'm going to put that my bacteria is in millions. Okay, so A, write a differential equation that expresses the relationship. So again, my rate of change, so my rate of change of bacteria at a time, is directly proportional to the number of bacteria. Alright, B, solve the differential equation for the number of bacteria as a function of time. Again, we can do our shortcut. And our shortcut, let me scroll up a little bit here. My shortcut is that my function is equal to my initial e to the k t. Now I've got to figure out what my initial is there. Did they give me any information yet? No, not yet. Okay. This is my initial. I don't know, maybe it'd be better to write it with that B naught to represent the initial. Either one. Okay, so now C, they give us information so we can actually solve. So again, most likely on the AP test, they're going to go straight to something like this. Suppose that initially there are 3 million bacteria, and 3 hours later the number has doubled. Write the particular equation that expresses the number of millions of bacteria as a function of hours. Okay, so again, here's our equation. They tell us initially there are 3 million bacteria. So this is my initial. Now I already have that my bacteria is in millions, so this would just be 3, right?
Yeah. Yeah.
Okay. Initially there's 3 million, and 3 hours later, so that's my time, the number has doubled. So my initial was 3 million. If it's doubled, how much bacteria do I have? 6 million. So it's 6. Okay. So let's go ahead and solve for our k. Divide both sides by 3, I get 2 equals e to the 3. Now to log both sides, so I get k is natural log of 2 divided by 3. This is what you would write if it was a non-calculator question. Punch on your calculator though, what do we get? 0.231. Now again, store that in for alpha k. Okay, D, I don't know that I've ever seen them ask this, but it says sketch the graph of time versus bacteria for 10 hours. Alright. Well, we know that at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Honestly, the easiest way to do this is they told us that at 3 hours we had how much? 6, right? What was my initial amount? 3. Let's do that. We're just sketching the graph. Again, it's an exponential curve. We know it goes for those 2 points. Alright, so E, what will the bacteria population be 1 full day after the first measurement? Okay, so this is probably what AP would ask. So we've got our equation. Oh, guys, I never finished writing the equation over here. I apologize. We found our K value, but we didn't actually write the equation. So my equation would be bacteria equals my initial, which was 3, e to the, and my K was 0.231. Okay. So I'm going to use that equation now. So the bacteria population would be 1 full day after first measurement. If I'm looking at 1 full day, what's my time going to be? 24, because we measured it in hours. Alright, so 3e to the 0.231 times 2. And again, you were using the full long decimal. Okay, so you're using the full natural log of 2 divided by 3. If this was non-calculator, you wouldn't be writing 0.231, you'd be writing natural log of 2 divided by 3. Alright, what do we get for the approximate number of bacteria?
768.
And that's a million, isn't it? That's a lot of bacteria.
Well, they're really small.
That is true. I wonder how much that would be. Size of a quarter? Size of a dollar? Oh, it's like a nickel. Oh, okay. Thank you for that clarification. All right. And then F, how long will it take the population to grow from 1 million to 2 million? We don't technically need a equation for this. All right, so how long will it take the population to grow from 1 million to 2 million? Does anyone think they know the answer right now? No? Okay, we'll do it the long way. 2 days. After 1 day, we had 768 million.
Well, yeah, because in 1 day it didn't. I'm gonna say 4 days. Wait, so are you saying?
Wait, we're talking about 1 billion. We just want to go from 1 billion to 2 billion. Here I went from 3 billion to 768
10 hours.
million. Oh wait. Oh, it's a billion. We're talking about billion. Okay. We'll just go and use our equation. All right. So let's use our equation. So our final would be 2 billion. How many millions is 2 billion?
100.
Wait, 2
2 billion.
Sorry.
Yeah. Is it 200 or 2,000?
Wait, what?
No.
2000.
Well, it depends on how many bacteria
Yeah, I think it would
because the
be.
bacteria phase is exactly.
Okay. This is a million, right?
Oh, you are.
How many?
You have 1,000.
How many? Yeah, the full thing's a billion. This first part's a billion, right?
Yeah.
How many millions is a billion? 1,000. We have 1,000 millions. 1,000 times 1 million. Okay, so maybe it would just have been better for us to write out 2 billion. All right, so 2,000 millions is our final. And now we have our initial is 1 billion, so 1,000 millions. Our rate is still the same, e to the 0.231 t. Again, this is the long decimal. When I divide, do you guys agree I get 2 equals e to the 0.231 t? We're doing natural log on both sides. Wait a second, what was the 0.231? Natural log of 2/3. Guys, when we solve, what do we get for t? 3. Why is it 3? 3 hours. What's Sebastian?
Because that's where we got 0.23 from.
Yeah, it's okay. So isn't 1 billion to 2 billion just doubling it?
Yeah.
Up here, how long did it take to go from 3 billion to 6 billion? It took 3 hours. Chelsea, you were spot on. So this one you technically didn't need to use your exponential because we knew that it took 3 hours. 3 hours to double. And this was just asking doubling. I mean, AP is not going to be that nice, but we did have to do it. Okay, go ahead, go to the bathroom, come back. Oh wait, no, real quick, G. Why isn't the world overwhelmed with bacteria? That's a lot of
We
bacteria.
wash our hands.
Because we wash our hands out like that.
Overwhelmed bacteria.
There is a lot of bacteria. Bacteria dies just as quickly as it
Oh, yeah.
Right, right?
But there's good bacteria too.
To make you think. Okay, now go leave bathroom and then come back to sleep.
So if it's like x with 68 billion, is that like acceptable? And so do you have to write out all the zeros?
Oh no, you can use the words million, billion, and whatnot. Yeah, you don't have to write out all the zeros. I think they would prefer if you didn't write out all the zeros.
Say what?
Okay, guys. I do want to take a look at one more chunk of this before we transition to standard. So if you would turn in your packet to where'd it go? Turn in your packet to where it says exponential growth continuation class 1. There's one thing I want to show you. We're almost there. We're like 5 minutes away from the end. It's printed weird. We can say stable wrong. Whatever. Okay, so turn in your notes to this. Exponential growth continuation class work. So I just want to draw your attention to something with this. So everything, we said we can use this shortcut when we have directly proportional. So keep in mind that's only for directly proportional. If it's not directly proportional, we can't use that shortcut. Okay, so for example, if it says the rate of change of y is proportional to 4y, then our rate of change of y, if it's proportional 4y, then we have our constant times 4y. Okay. If the rate of change is proportional to 4 minus y, our rate of change of y is proportional to 4 minus y. If it's inversely proportional, our rate of change is inversely proportional, so that's when we have 1 over y, so you can either write it as k over y, or you can write it as k times y. Okay. And then if it was proportional to square root of y, that'd be k times square root of y. Okay. So this shortcut only works when it's directly proportional. So if it doesn't say that, then we can't use that shortcut. So for example here, our example, it says that the water's height, this is h, I hope it says h, changes, the rate at which the water's height changes is directly proportional to the square root of its height. When we go to write our equation, then our rate of change of the height, dh dt, is proportional to the square root. We would have to write k, the square root of its height, square root of h. So when we go to do our differential equation, like for C, where it says solve the differential equation, we can't use the shortcut. We have to go back to doing what we did with our separable differential equations. Okay, so you have to actually multiply by dt, get the h's on one side, the t's on the other, and then take your integral. Okay, so this would be going back to the old way. What we did last class. Okay. So in B you would have solved and we would have gotten, actually let's just do it real quick. So it says suppose that at time t, the height is 20 centimeters and the ht is -5. Alright, so the ht is -5. We don't know k. The height is 20 centimeters. Find the value of k, so we would solve. We get, so divide by square root of 20. Come on, let's break up that square root of 20. What does square root of 20 equal? 2/5. Oh, I guess nothing simplifies. That's it. All right, so we'd have then that k equals -5 over 2√5. So when we go to do our differential here, -5 over 2√5. I would have to go back to my old way where I get my t's on one side, h's on the other. So I would then have, I would divide both sides by root h, and multiply by dt. So I'd have dh over root h equals -5 over 2√5 times dt. And then we would just go back to integrating and doing like we did before. Okay, so if it's not directly proportional, you can't take the shortcut. You have to go back to the old way. Okay, I just want to make you aware of that. All right, so again, in summary, what we did is that whenever our function says, whenever our prompt says that it is directly proportional, something is directly proportional to itself, so the rate is directly proportional to itself, that's when we can use our shortcut. And again, our shortcut is dy dt. Y is y equals our initial. Okay, so your homework, let's just do, what do you guys want, odds or evens? You know what? I'll let you choose. Either do odds or evens of the ones that say homeworks. How about that? No. Right, that's why I said no. Okay, so let's just do odds or evens of the ones that say homework. You don't have to do classwork. Questions with that? Chelsea? Yes. Okay, so your homework, odds or evens, whichever you want, to half of the homework. Okay, so Stinger, again, you can work on your project. I'm going to get out my list of all the prompts and tell you which one you have. Also, to have your Unit 6 test to give back to you. So, let me do that first.
Oh my god.
Nope, I can put it on there though. I'll put it on SIS first, then give it back to you. Then we'll get the prompts. In the meantime, you are welcome to work on your cross-sections project, work on your homework, whatever you would like.